Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. How asteroids can have their own moons. The first asteroid moon was discovered in 1993, when the Galileo spacecraft, on its way to Jupiter, flew past an asteroid named Ida and transmitted images showing a small companion orbiting it. The discovery surprised many scientists. Ida itself is only about 56 kilometers long, an irregular, potato-shaped chunk of rock tumbling through space. Its tiny moon, later named Dactyl, measures merely 1.4 kilometers across. How could such a small object, with such weak gravity, possibly hold onto a moon? This discovery opened an entirely new chapter in our understanding of asteroids, revealing that these ancient fragments of the early solar system are far more complex and dynamic than anyone had imagined. The key to understanding asteroid moons lies in recognizing that gravity, no matter how weak, still operates according to the same laws, whether you're considering a massive planet or a tiny asteroid. Every object with mass generates a gravitational field, and that field extends infinitely into space, weakening with distance, but never disappearing entirely. An asteroid's gravity is incredibly feeble compared to a planet's. Ida's surface gravity is only about 0.3 to 1% of Earth's, depending on where you measure it, on the irregular surface. But this tiny gravitational pull is sufficient to influence nearby objects, and under the right circumstances, it can capture and hold a moon in orbit. The mechanics of orbital motion around an asteroid differ significantly from orbits around planets. Planets are generally spherical, or nearly so, which means their gravitational fields are relatively simple. They approximate the field of a point mass located at the planet's center. Asteroids, however, are often highly irregular, shaped like elongated potatoes, peanuts, or even contact binaries where two lobes are stuck together. This irregular shape creates a complex gravitational field with multiple peaks and valleys, regions where the gravitational pull is stronger or weaker than average. An object orbiting an irregular asteroid doesn't follow a simple ellipse the way a planet orbits the Sun. The orbit wobbles and shifts due to the uneven gravity field. Additionally, most asteroids rotate, and this rotation causes the gravitational field to change over time from the perspective of an orbiting object. The combination of irregular shape and rotation creates a challenging environment for stable orbits. Yet despite these complications, asteroid moons not only exist but are surprisingly common. Current estimates suggest that about 15% of near-Earth asteroids have companions, and the fraction is even higher among certain populations. Asteroid moons form through several mechanisms, each revealing something about the dynamic processes that shape these small bodies. The first mechanism is capture. Similar to how planets can capture moons, though the process works differently at asteroid scales. When two asteroids pass close to each other, they normally just fly past, perhaps exchanging some momentum through gravitational interaction, but remaining on separate trajectories. However, if a third body is nearby during the encounter, it can absorb some of the kinetic energy through a three-body gravitational interaction, allowing one asteroid to be captured into orbit around the other. This three-body capture was more common in the early solar system, when asteroids were more numerous and encounters more frequent. The asteroid belt, located between Mars and Jupiter, contains hundreds of thousands of asteroids larger than 1 kilometer and millions of smaller ones. In the denser environment of the early solar system, close encounters between 3 or more asteroids occurred regularly, providing opportunities for capture. Once captured, the orbit would gradually stabilize through tidal interactions and additional gravitational perturbations. Collisions represent another pathway to moon formation. The asteroid belt is a violent place where collisions occur regularly on geological timescales. When two asteroids collide, the impact doesn't necessarily destroy both objects. Depending on the impact velocity and angle, a collision might excavate a crater and eject material into space. Some of this ejected material falls back onto the asteroid, but some of it enters orbit around the shattered parent body. Over time, these orbiting fragments can collide with each other and coalesce into a moon. The collision scenario explains why many asteroid moons orbit very close to their parents and have compositions similar to the parent asteroid. If a moon formed from impact debris, it would naturally be made of the same material as the parent. Studies of asteroid pairs, asteroids with very similar orbits and compositions, suggest that many originated as fragments from catastrophic collisions that split a parent asteroid into two or more large pieces. In some cases, these pieces remain gravitationally bound, creating a binary asteroid system. The YORP effect provides a third mechanism for creating asteroid moons, and it's one of the most fascinating processes in asteroid dynamics. YORP stands for Yarkovsky-O'Keefe-Radzievsky-Paddock, named after the scientists who contributed to understanding this phenomenon. The YORP effect occurs when sunlight reflecting off an asteroid's irregular surface creates tiny torques that gradually change the asteroid's rotation rate. The effect is incredibly small. It might change an asteroid's rotation period by only milliseconds per year, but over millions of years, these tiny changes accumulate. As the YORP effect spins an asteroid faster and faster, centrifugal forces at the equator increase. Eventually, the asteroid might be rotating so fast that material at the equator experiences outward centrifugal forces that exceed the inward gravitational forces. At this point, material begins to lift off the surface and enter orbit, forming a ring or disk around the asteroid. This orbiting material can then aggregate into one or more moonlets. Computer simulations and observations of very rapidly rotating asteroids support this mechanism. Asteroid 1999 KW4 provides a clear example of the YORP effect in action. This binary asteroid system consists of a larger primary asteroid, about 1.3 kilometers in diameter, rotating once every 2.8 hours, extremely fast for an object this size. A smaller satellite, about 360 meters across, orbits the primary at a distance of about 2.6 kilometers. The primary asteroid has a distinct equatorial ridge, exactly what would be expected if centrifugal forces had been pushing material toward the equator. The satellite likely formed from material that was flung off this equatorial region when the primary was spinning even faster in the past. The rotation rates of asteroids play a crucial role in their ability to hold moons. There's a limiting rotation rate, typically around one rotation every 2 to 3 hours for a solid asteroid, beyond which centrifugal forces would tear the asteroid apart. This limit, called the critical spin limit, depends on the asteroid's size, shape, and material strength. Asteroids can spin faster than this limit only if they're held together by internal strength, essentially solid rocks, rather than just gravity. Many asteroids appear to be rubble piles, loose aggregations of boulders and gravel, held together primarily by their own weak gravity, with little internal strength. These rubble pile asteroids cannot spin faster than the critical limit without shedding material or breaking apart. The Roche limit becomes relevant for asteroid moons, just as it does for planetary moons. The Roche limit is the distance inside which tidal forces would tear apart a satellite that's held together only by its own gravity. For solid objects held together by material strength, they can orbit inside the Roche limit without being destroyed, though they experience severe tidal stresses. Many asteroid moons orbit near or even slightly inside the classical Roche limit for a fluid body, suggesting that they're solid objects with sufficient strength to resist tidal disruption. Binary asteroids, where two similarly sized objects orbit their common center of mass, represent a special category. In these systems, neither object is clearly the moon of the other. They're more like double asteroids, co-orbiting companions. The Pluto-Charon system is arguably a binary system, though Pluto is now classified as a dwarf planet rather than an asteroid. Among smaller asteroids, binary systems are not uncommon. The asteroid Antiope consists of two objects, each about 88 kilometers in diameter, orbiting their common center of mass at a separation of about 170 kilometers. These binary systems likely form from gentle collisions or from the splitting of a rapidly rotating parent body. When an asteroid spins fast enough, it can develop a dumbbell or peanut shape, elongated along its equatorial plane. If the spin increases further, the dumbbell can split at its narrow center, creating two separate bodies. Because they formed from the same parent, they initially have very similar velocities and remain gravitationally bound, orbiting each other. Observing asteroid moons requires careful astronomical work. Most asteroids are too small and distant to be resolved as disks even through powerful telescopes. They appear as points of light. Their moons are even fainter and closer to the primary, making direct imaging challenging. However, several techniques reveal their presence. Light curve analysis measures how an asteroid's brightness changes over time as it rotates. A simple asteroid produces a regular, repeating pattern, but if a moon is present, it creates additional dips or bumps in the light curve as it passes in front of or behind the primary asteroid, or as it reflects additional light toward Earth. Radar observations provide another powerful technique. When radio waves are bounced off an asteroid, the reflected signal contains information about the asteroid's shape, rotation, and surface features. If a moon is present, it appears as a separate echo in the radar data, delayed relative to the primary's echo by the light travel time to the more distant moon. The Arecibo Observatory in Puerto Rico and the Goldstone Solar System Radar in California have discovered dozens of asteroid moons through radar observations of near-Earth asteroids as they pass relatively close to Earth. Spacecraft missions provide the most detailed views of asteroid moons. After Galileo's discovery of Dactyl orbiting Ida, subsequent missions have encountered other asteroid systems. The Near-Shoemaker spacecraft orbited asteroid Eros, which has no moon, but provided detailed information about asteroid composition and structure that helped interpret observations of binary systems. The Dawn mission visited the large asteroids Vesta and Ceres, also moonless, but revealed the complex geology of these protoplanets. Future missions specifically targeting binary asteroids will provide unprecedented insights into these systems. The existence of asteroid moons has practical implications beyond pure science. Some near-Earth asteroids pose potential collision hazards to Earth, and understanding whether they have moons affects how we might deflect them if necessary. A binary asteroid system behaves differently than a single asteroid when subjected to external forces. The NASA DART mission, launched in 2021, deliberately crashed a spacecraft into Dimorphos, the moon of the asteroid Didymos, to test whether kinetic impacts could alter an asteroid's orbit, a potential planetary defense technique. The mission successfully changed Dimorphos's orbital period, demonstrating that asteroid moons respond to impacts in measurable ways. The orbital dynamics of asteroid moon systems are surprisingly rich because the gravitational fields are so weak. Other forces become relatively more important. Solar radiation pressure, the physical push exerted by sunlight, can perturb asteroid moon orbits significantly over time. The orbits slowly evolve, sometimes becoming more circular, sometimes more elliptical, depending on the specific configuration. Tidal forces between the asteroid and its moon, though tiny, gradually exchange angular momentum, causing the Moon to migrate inward or outward over millions of years, potentially leading to eventual escape or collision. Triple asteroid systems exist as well, where one asteroid has two moons, or where three similarly sized bodies orbit their common centre of mass. The asteroid Sylvia, about 260 kilometres in diameter, has two known moons named Romulus and Remus, discovered in 2001 and 2004 respectively. Romulus orbits at about 1,360 kilometres from Sylvia, with an orbital period of 3.6 days. Remus orbits closer, at about 710 kilometres, with a period of 1.4 days. These multiple moon systems provide natural laboratories for studying gravitational dynamics in the weak field limit. The study of asteroid moons illuminates the processes that operated during planet formation. Planets grew through collisions and mergers of smaller bodies, asteroids, and planetesimals. Understanding how these small bodies interact, collide, capture each other, and form bound systems helps us understand the early stages of planet formation. Every asteroid moon is a relic of these ancient processes, a small-scale version of the interactions that built planets from swarms of orbiting debris billions of years ago. The discovery that asteroids can have moons transformed them from simple rocks floating in space into complex, evolving systems with their own orbital dynamics, formation histories, and future fates. These tiny moons orbiting tiny worlds demonstrate that the fundamental laws of gravity and motion operate at all scales, creating structure and dynamics from the largest galaxy clusters down to kilometre-sized rocks tumbling through the asteroid belt. Each small moon a reminder that even the weakest gravity can bind objects together across the emptiness of space. How gravity bends light in space. Light travels in straight lines through empty space, or at least that's what our everyday experience suggests. A laser beam shoots across a room in a perfectly straight path. Starlight reaches Earth from distant stars without deviating from its course. But this intuition breaks down when gravity becomes involved. In the presence of massive objects, light follows curved paths, bending around stars, galaxies, and even clusters of galaxies in ways that reveal one of the most profound insights about the nature of space, time, and gravity itself. The story begins with Albert Einstein's general theory of relativity, published in 1915, which fundamentally reimagined what gravity is. Newton had described gravity as a force. Masses attract each other across distance through some invisible pull. Einstein proposed something radically different. Gravity, he suggested, is not a force at all, but rather a consequence of the geometry of space-time itself. Massive objects don't pull on other objects. Instead, they warp the fabric of space-time around them, and objects simply follow the straightest possible paths through this curved geometry. Imagine space-time as a stretched rubber sheet. Place a bowling ball on the sheet, and it creates a depression, warping the flat surface into a curved shape. Now roll a marble across the sheet near the bowling ball. The marble's path curves as it moves through the depression, not because the bowling ball is pulling on it, but because the surface itself is curved. The marble is still following the straightest path it can, what mathematicians call a geodesic, but in curved space, straight lines look curved to outside observers. This is what happens with light near massive objects. The light is following a geodesic through space-time, travelling along the straightest possible path. But because space-time itself is curved by the presence of mass, that path appears curved when viewed from our perspective. The light isn't being pulled by gravity in the Newtonian sense. It's simply following the geometry of space-time, which has been warped by mass. The amount of bending depends on two factors: the mass of the object doing the bending and how close the light passes to that mass. More massive objects create deeper curves in space-time, causing more dramatic bending. Light passing closer to a mass experiences stronger curvature than light passing farther away. For most objects we encounter in daily life, this bending is utterly negligible, far too small to detect. Even for something as massive as Earth, the bending of light is minuscule. A beam of light grazing Earth's surface would bend by less than 1,000th of a degree. But consider the Sun. With a mass 333,000 times greater than Earth, the Sun creates a significant warp in space-time around it. Light from a distant star passing close to the Sun's surface is deflected by about 1.75 arc-seconds, a tiny angle equal to roughly the width of a quarter viewed from 2 miles away, but measurable with careful observations. This prediction of general relativity was first confirmed during a solar eclipse in 1919, when stars near the Sun's position in the sky appeared slightly displaced from their normal locations. The Sun's gravity had bent their light as it passed by, making the stars appear to be in slightly different positions than they actually were. This gravitational bending of light becomes dramatically more pronounced around more massive and compact objects. A neutron star, containing more mass than the Sun, compressed into a sphere only about 12 miles across, creates such severe space-time curvature that light from the far side of the star can bend around it and reach an observer on the opposite side. You could theoretically see more than half of the star's surface at once because light from behind curves around to the front. Black holes represent the extreme limit of gravitational light bending. At the event horizon of a black hole, space-time is curved so severely that light emitted outward from that surface is bent back inward. The escape velocity at the event horizon equals the speed of light, which is another way of saying that space-time curvature there is so extreme that even light following its straightest possible path still curves back toward the black hole. Just outside the event horizon, there's a region called the photon sphere, where light can orbit the black hole in unstable circular paths, bent continuously by the intense curvature of space-time. The shadow of a black hole, the dark region we see in images like the famous Event Horizon Telescope, picture of M87's supermassive black hole, exists because of this extreme light bending. Light that passes close enough to the black hole is captured, unable to escape, creating a dark silhouette. The bright ring surrounding this shadow is light from the accretion disk that has been bent and focused by the black hole's gravity, with some photons having orbited partway around the black hole before reaching the observer, creating multiple images overlaid on each other. Gravitational lensing occurs when light from a distant object passes near a massive object on its way to Earth. The massive object acts as a lens, bending the light and focusing it toward Earth, just as a glass lens bends and focuses light. Galaxies and galaxy clusters containing hundreds of billions or even trillions of times the Sun's mass are particularly effective gravitational lenses. When a massive galaxy cluster lies between Earth and a more distant galaxy, the cluster's gravity bends light from the background galaxy, often creating multiple images, arcs, or even complete rings. Einstein predicted a specific case called an Einstein ring, which forms when the lensing mass, the background light source, and the observer are perfectly aligned. In this configuration, the background object's light is bent equally in all directions around the lensing mass, creating a circular ring of light. Perfect Einstein rings are rare because perfect alignment is unlikely, but numerous partial rings and arcs have been observed where the alignment is close, but not exact. Strong gravitational lensing creates multiple images of the same background object. Light from the source can take different paths around the lensing mass, arriving at Earth from different directions. An observer sees the same galaxy or quasar in multiple locations in the sky simultaneously, each image distorted differently depending on the path the light took. By analysing these multiple images, their positions, brightness and distortions, astronomers can map out the distribution of mass in the lensing object, including the dark matter that can't be seen directly. One of the most famous examples of gravitational lensing revealed itself in the Hubble Deep Field images. A massive galaxy cluster acts as a natural telescope, magnifying and brightening galaxies far behind it. Some of the most distant galaxies ever observed were discovered this way, their light amplified by gravitational lensing to the point where even these incredibly faint, distant objects become visible. Without the magnification provided by the intervening cluster's gravity, these galaxies would be too faint to detect, even with our most powerful telescopes. Weak gravitational lensing is a more subtle effect. Rather than creating obvious multiple images or dramatic arcs, weak lensing slightly distorts the shapes of background galaxies. Each galaxy is stretched and sheared by a tiny amount, usually only a few percent. Individual distortions are impossible to distinguish from the galaxy's natural shapes, but by measuring the shapes of thousands or millions of galaxies and looking for statistical patterns in their distortions, astronomers can map out the distribution of matter, including dark matter, along the line of sight. This technique has become one of the most powerful tools for studying dark matter distribution in the universe. Gravitational lensing also affects the apparent brightness of objects. When a massive object passes between Earth and a more distant star, the foreground object's gravity can focus the background star's light, temporarily brightening it. This gravitational microlensing is used to detect exoplanets. When a star passes in front of another star, the foreground star's gravity creates a brief brightening lasting days to weeks. If the foreground star has a planet, the planet's gravity creates an additional, brief spike in brightness, revealing its presence even though the planet itself is far too faint to see directly. The time light takes to travel along different paths around a gravitational lens can vary. Light taking a longer path around one side of a lensing galaxy arrives later than light taking a shorter path around the other side. For variable sources like quasars, which change in brightness over time, this time delay becomes observable. A brightening in one image of a lensed quasar will appear days, weeks, or months before the same brightening appears in another image, the delay corresponding to the difference in light travel time along the different paths. Measuring these time delays allows astronomers to determine distances to the lensed objects and constrain cosmological parameters like the universe's expansion rate. Space-time curvature near massive objects doesn't just bend light spatially, it also affects light's frequency through gravitational redshift. Light climbing out of a gravitational well loses energy, shifting to longer wavelengths and lower frequencies. Photons emitted from the surface of a white dwarf, neutron star, or near a black hole arrive at Earth redshifted compared to identical photons emitted far from any massive object. This gravitational redshift is distinct from the Doppler shift, caused by motion. It's a consequence of how time itself runs slower in stronger gravitational fields. The ability of gravity to bend light provides one of the most direct ways to test general relativity. Every observation of gravitational lensing confirms Einstein's predictions about how space-time curvature works. The precise angles at which light bends, the patterns of multiple images, the time delays between images, and the gravitational redshift all match the predictions of general relativity with remarkable accuracy. Alternative theories of gravity make different predictions, and so far, every test has vindicated Einstein's century-old theory. Gravitational lensing has become an essential astronomical tool. It allows us to study the distribution of dark matter by observing how it lenses background galaxies. It magnifies distant galaxies, enabling studies of the early universe that would otherwise be impossible. It reveals exoplanets orbiting distant stars. It measures cosmic distances and the expansion rate of the universe. All of this is possible because massive objects warp spacetime, and light faithfully follows the curves and valleys of that warped geometry. The universe is filled with matter, and that matter curves space-time everywhere. Light from the most distant galaxies has travelled billions of years to reach Earth, passing countless galaxies, galaxy clusters, and vast expanses of dark matter along the way. Every massive structure the light passes deflects it slightly, creating a cosmic hall of mirrors where every photon's path is bent and redirected many times. The images we see in our telescopes are not straight-line projections from their sources, but rather the accumulated result of countless tiny deflections as light navigates the curved space-time of our universe. The geometry of the universe itself, on the largest scales, also affects how light travels. If the universe has overall positive curvature, like the surface of a sphere, light paths will eventually converge. If it has negative curvature, like a saddle shape, light paths diverge. Current observations suggest the universe is nearly flat on the largest scales, meaning that, on average, over distances spanning billions of light years, light travels in straight lines. But locally, around every massive object from planets to galaxy superclusters, space-time curves, and light follows those curves, revealing the intimate connection between matter geometry and the paths that light traces through the cosmos. How fast you'd need to go to leave a planet. Every object massive enough to have significant gravity holds onto anything near its surface. A ball thrown upward eventually falls back down. A bird must constantly flap its wings to stay aloft. Even the fastest jet aircraft cannot fly into space. Eventually it runs out of altitude and must descend. To truly leave a planet, to escape its gravitational grip entirely and coast into space without using any more fuel, you must reach a specific speed called escape velocity. This critical speed depends on the planet's mass and size, and understanding it reveals why launching rockets is so difficult, why some worlds can hold atmospheres while others cannot, and why the smallest push can send an astronaut drifting away from an asteroid while escaping Earth requires enormous rockets burning millions of pounds of fuel. Escape velocity is not about reaching a particular altitude or getting above the atmosphere. It's about speed, specifically moving fast enough that your kinetic energy equals or exceeds the gravitational potential energy binding you to the planet. If you launch something straight up at exactly escape velocity, it will climb higher and higher, slowing down continuously as gravity pulls it back, but never quite stopping. It will coast to infinite distance, arriving there with zero velocity, having converted all its initial kinetic energy into potential energy. Launch at any speed less than escape velocity, and gravity eventually wins, pulling the object back down. For Earth, escape velocity at the surface is about 11 kilometers per second, roughly 40,000 kilometers per hour, or about 25,000 miles per hour. This is more than 30 times faster than a typical passenger jet flies. To reach this speed, starting from rest requires enormous amounts of energy, which is why rockets are so large and burn so much fuel. The Saturn V rocket that launched Apollo missions to the Moon stood over 100 meters tall and weighed more than 2,000 tons at launch. But only about 50 tons of that mass, less than 3%, was the actual Apollo spacecraft and crew. Everything else was fuel and engines needed to accelerate that relatively small payload to the speeds necessary for spaceflight. Escape velocity depends on two factors: the planet's mass and its radius. More massive planets have higher escape velocities because stronger gravity pulls harder, requiring more speed to escape. Larger planets, meaning planets with larger radii, have lower escape velocities at their surfaces because you start farther from the center of mass where gravity is weaker. Earth is more massive than Mars, but also larger, and the combination means Earth's escape velocity is about 4.5 kilometers per second, higher than Mars's escape velocity of roughly 5 kilometers per second. This makes Mars somewhat easier to launch from than Earth. A rocket leaving Mars needs to reach only about half the speed required to leave Earth, which translates to roughly 1/4 the energy. Energy requirements scale with the square of velocity. Mars's thinner atmosphere also helps, creating less air resistance during ascent. These factors make Mars an attractive location for future space missions that might launch from the surface to explore the outer solar system or return to Earth. The Moon, much smaller and less massive than Earth, has an escape velocity of only about 2.5 kilometers per second, less than 1/4 Earth's escape velocity. This made the Apollo lunar module's ascent from the Moon's surface relatively straightforward compared to launching from Earth. The ascent stage needed far less fuel and could use a much smaller engine. The low escape velocity also meant that the lunar module could take off without the massive multi-stage rockets required for Earth launch, using a single engine to reach lunar orbit directly. Jupiter, the most massive planet in our solar system, has an escape velocity from its cloud tops of about 60 kilometers per second, more than 5 times Earth's escape velocity. Launching from Jupiter, if there were a solid surface to launch from, would require vastly more energy than launching from Earth. Any spacecraft falling into Jupiter's atmosphere would need extraordinary speeds to escape again, which is why missions to Jupiter use gravity assists from other planets to gain speed rather than attempting to enter and exit Jupiter's deep gravity well. The concept of escape velocity explains why planets can hold atmospheres, while asteroids and comets cannot. Gas molecules in an atmosphere move at speeds related to temperature. Hotter gases move faster. For an atmosphere to remain bound to a body over billions of years, the typical speed of atmospheric molecules must be significantly lower than escape velocity. If molecules regularly reach speeds close to or exceeding escape velocity through random thermal motion, they leak away into space. Earth's atmosphere consists primarily of nitrogen and oxygen molecules that move at average speeds of a few hundred meters per second at normal temperatures, well below escape velocity. The lightest element, hydrogen, moves much faster at the same temperature because lighter molecules move faster for a given thermal energy. Hydrogen molecules at Earth's atmospheric temperature move at average speeds around 2 kilometers per second, which is still well below escape velocity, but close enough that over billions of years, Earth has lost most of its primordial hydrogen. The Moon's escape velocity is low enough that essentially no gas can remain in a lunar atmosphere. Any molecules would need to be extremely cold to have velocities below escape velocity, but solar heating warms the lunar surface during the long lunar day, giving molecules enough energy to escape. This is why the Moon has no atmosphere. Its weak gravity cannot hold even the lightest gases against thermal evaporation. Mars, with escape velocity between the Moon's and Earth's, represents an intermediate case. Mars can hold heavier molecules, like carbon dioxide in its atmosphere, but it loses lighter molecules more easily. Mars also lacks a strong magnetic field to protect its atmosphere from the solar wind, the stream of charged particles from the Sun. Over billions of years, the solar wind has stripped away most of Mars's original atmosphere, leaving the thin atmosphere we observe today. Escape velocity decreases with altitude. At the surface, you need to reach Earth's full escape velocity of 11 kilometers per second. But at the altitude where the International Space Station orbits, about 400 kilometers up, escape velocity is slightly less, around 10.9 kilometers per second. The difference is small because 400 kilometers is not much compared to Earth's radius of about 6,400 kilometers. But at lunar distance, about 380,000 kilometers, escape velocity from Earth has dropped to only about 1 kilometer per second. Apollo spacecraft needed to reach only this lower speed to escape Earth's gravity after coasting most of the way to the Moon. Escape velocity is the same in all directions. You could launch straight, up, horizontally, or at any angle, and you'd need the same speed to escape. The direction doesn't matter for escape, only the speed. However, in practice, rockets don't launch straight up. They curve their trajectory to gain horizontal velocity as well as altitude, because horizontal velocity is what's needed for orbit. Reaching escape velocity while moving horizontally means you escape while also having momentum that carries you away from the planet. rather than climbing straight up until you barely escape with zero velocity. Black holes represent the extreme case of escape velocity. At the event horizon, the boundary of a black hole, escape velocity equals the speed of light. Nothing can move faster than light, so nothing can escape from within the event horizon. This is what makes a black hole black. Not even light can escape once it crosses this boundary. For a black hole with a few times the Sun's mass, the event horizon has a radius of only about 10 kilometers. The extreme compression of mass into such a small radius creates escape velocities that reach and exceed the cosmic speed limit. Interestingly, you don't have to reach escape velocity to get into space. Rockets reaching orbit around Earth need to achieve only about 8 kilometers per second at orbital altitude, less than escape velocity. Orbital velocity is the speed at which your sideways motion exactly balances gravitational pull, so you continuously fall around the planet rather than falling back to it. This is easier to achieve than escape velocity, which is why orbital missions are more common than interplanetary missions. The Space Shuttle, for example, accelerated to about 8 kilometers per second to reach low Earth orbit, then used additional fuel to accelerate to higher speeds only when needed for missions to higher orbits or to the International Space Station. Missions leaving Earth orbit for the Moon, Mars, or other destinations required additional speed beyond orbital velocity to reach escape velocity and break free of Earth's gravity. Understanding escape velocity also explains how gravity assists work. When a spacecraft flies past a planet on a carefully calculated trajectory, it can gain speed by essentially stealing a tiny amount of the planet's orbital momentum. From the spacecraft's perspective, it falls toward the planet, swings around it, and flies away. If the trajectory is chosen correctly, the spacecraft leaves moving faster relative to the Sun than it arrived, having been accelerated by the planet's gravity without burning any fuel. The Voyager spacecraft used multiple gravity assists from Jupiter and Saturn to reach speeds high enough to eventually escape the solar system entirely, crossing into interstellar space decades after launch. Calculating how fast you'd need to go to leave a planet comes down to a simple formula involving the planet's mass and radius, derived from Newton's law of universal gravitation. The energy required to escape grows with planetary mass and shrinks with planetary radius, creating the variety of escape velocities we observe throughout the solar system. From tiny asteroids where you could literally jump into space if you weren't careful, to massive Jupiter where even the most powerful rockets would struggle to escape, the speed required to leave a world tells us about that world's fundamental properties and shapes everything from how we design spacecraft to which worlds can hold atmospheres, determining the accessibility of each destination in our cosmic neighborhood and beyond. How extraterrestrial plants could photosynthesize. Photosynthesis, the process by which plants, algae, and certain bacteria capture light energy and convert it into chemical energy, powers most of Earth's ecosystems. Green plants absorb sunlight, split water molecules, combine carbon dioxide from the air with hydrogen from the water, and produce sugars while releasing oxygen as a byproduct. This process transformed Earth's atmosphere from oxygen-poor to oxygen-rich over billions of years, enabling the evolution of complex animal life. Photosynthesis seems so central to life that we naturally wonder whether alien plants on distant worlds would photosynthesize in similar ways. The answer is nuanced. While capturing energy from starlight would likely be advantageous for life on any illuminated world, the specific chemistry and mechanisms of alien photosynthesis would differ dramatically depending on the star's properties, atmospheric composition, available pigments, and evolutionary history of each world. On Earth, photosynthesis centers on chlorophyll, a complex molecule containing magnesium at its center, surrounded by a ring structure that absorbs light strongly in the red and blue portions of the spectrum, while reflecting green light, which is why plants appear green. Chlorophyll's absorption spectrum is not random but reflects the properties of sunlight. Our Sun is a yellow dwarf star with a surface temperature around 6,000 degrees Celsius, emitting light most strongly in the visible portion of the spectrum that our eyes evolved to see, with peak emission in the green-yellow range. Plants evolved pigments that absorb the abundant wavelengths while reflecting the less useful portions. But most stars in the galaxy are red dwarfs, cooler, smaller stars with surface temperatures around 3,000 degrees that emit most of their light in the red and infrared portions of the spectrum. A planet orbiting in the habitable zone of a red dwarf would receive much less visible light and far more infrared radiation than Earth receives from our Sun. Photosynthetic organisms on such a world would need to adapt to this shifted spectrum, likely evolving pigments that absorb infrared light rather than visible light. Capturing infrared photons presents challenges because each infrared photon carries less energy than a visible light photon. On Earth, chlorophyll uses 2 photons, absorbed at different stages of photosynthesis, to extract enough energy to split water molecules, which requires significant energy input. With lower energy infrared photons, alien photosynthesis might need to capture 3 or even 4 photons per reaction to gather sufficient energy, making the process less efficient. However, red dwarf stars are extremely common and extremely long-lived, shining for trillions of years compared to the Sun's 10 billion year lifespan. So even if photosynthesis is less efficient under red dwarf light, organisms would have enormous amounts of time to evolve and adapt. The pigments that absorb infrared light would likely appear black or very dark to human eyes because they would absorb nearly all visible light in addition to infrared. A forest on a red dwarf planet might be covered in black vegetation, maximizing absorption of every available photon from the dim red star. This is the opposite of Earth's green plants, which reject green light as insufficiently useful. On a planet where photons are precious, wasting any light would be disadvantageous, so evolution would favor organisms that capture everything. Conversely, planets orbiting hot, bright blue or white stars would receive intense ultraviolet radiation, along with visible and infrared light. Ultraviolet photons carry high energy, potentially too much energy, as UV light damages DNA and proteins. Photosynthetic organisms on such worlds might evolve pigments that specifically avoid ultraviolet absorption, reflecting or dissipating UV light while capturing only visible wavelengths. Or they might evolve protective mechanisms, UV-absorbing compounds in outer cell layers, extremely efficient DNA repair systems, or pigments that can safely handle high-energy photons by converting excess energy into heat or fluorescence. The color of alien plants would thus depend on their star's spectrum. Under orange K-type stars, plants might be red or orange, reflecting the most common light while absorbing other wavelengths. Under blue stars, plants might be yellow or orange. The specific colors would depend not just on what light is available, but also on what pigments evolution happens to discover and what combination of wavelengths provides optimal energy capture. Multiple pigments working together might be advantageous. On Earth, plants contain several pigments beyond chlorophyll, carotenoids, that absorb blue and green light, appearing yellow, orange, or red, and other accessory pigments that expand the range of useful wavelengths. These accessory pigments capture light that chlorophyll misses and transfer the energy to chlorophyll for use in photosynthesis. Alien plants might evolve even more diverse pigment systems, with perhaps 5 or 10 different pigments, each specialized for different wavelength ranges, collectively capturing a broader spectrum than Earth's photosynthetic organisms manage. The electron transport chains that actually convert light energy into chemical energy might use different chemistry than Earth's photosynthesis. On Earth, photosynthesis splits water molecules to extract electrons, releasing oxygen gas as waste. But water splitting is energetically demanding. It requires significant light energy input. An alien photosynthesis might use different electron donors that are easier to oxidize than water. Hydrogen sulfide, for instance, is easier to split than water and was likely used by early photosynthetic bacteria on Earth before oxygen-producing photosynthesis evolved. A planet with abundant hydrogen sulfide might develop photosynthetic life that remains at this stage indefinitely, producing elemental sulfur rather than oxygen as waste. Iron compounds, organic molecules, or even molecular hydrogen could serve as electron donors in alternative photosynthetic pathways. Each would produce different waste products. Iron photosynthesis might precipitate iron oxides. Organic-based photosynthesis might produce various carbon compounds, and hydrogen-based photosynthesis might produce protons that combine with other elements. None of these would generate an oxygen-rich atmosphere, demonstrating that photosynthesis doesn't necessarily equal oxygen production. The carbon source might also vary. Earth plants use carbon dioxide from the atmosphere as their carbon source, but CO2 concentrations vary dramatically across different worlds. Venus has a thick CO2 atmosphere, but is far too hot for life as we know it. Mars has thin atmosphere that's mostly CO2, but overall, CO2 availability is low due to the low pressure. A planet with very low atmospheric CO2 might require photosynthetic organisms that can concentrate and capture CO2 extremely efficiently, perhaps with specialized structures or enzymes far more effective than Earth's plants possess. Alternatively, alien photosynthesis might use carbon sources other than CO2. Carbon monoxide, methane, or even dissolved bicarbonate in water could provide carbon for building organic molecules. Each source would require different enzymatic machinery and would produce different end products. Methane-based photosynthesis might produce more complex hydrocarbons, essentially reversing the process that creates methane on Earth. ICO-based photosynthesis might build organic molecules through different chemical pathways than CO2-based photosynthesis uses. The physical structure of alien photosynthetic organisms might differ radically from Earth's plants. Trees evolved on land where structural support is needed to compete for sunlight, growing tall to shade competitors. But on a planet with perpetual dense cloud cover, blocking direct sunlight and providing only diffuse illumination, there would be no advantage to height. All locations would receive similar light levels. Plants might remain low-growing, perhaps forming dense mats rather than tall structures. On a planet with a very thin atmosphere, providing minimal structural support, perhaps Mars if it ever hosts photosynthetic life, organisms might need to be extremely sturdy and low-profile to withstand wind without atmospheric cushioning. Or on a high-gravity world, the structural challenges of growing tall might be prohibitive, keeping photosynthetic organisms close to the ground in spreading horizontal forms rather than vertical trees. Aquatic photosynthesis might dominate on ocean worlds. Earth's oceans contain vast amounts of photosynthetic organisms, phytoplankton, algae, and photosynthetic bacteria that drift or swim in the water column, capturing sunlight in the upper illuminated layers. On a world covered entirely by ocean, with no dry land, all photosynthesis would necessarily be aquatic. These organisms might evolve greater efficiency at capturing dim light filtered through water, or might develop gas-filled structures to regulate their depth, staying in the optimal light zone. Deep-sea photosynthesis might even be possible using not sunlight, but the faint light produced by hydrothermal vents or bioluminescence. On Earth, some photosynthetic bacteria near deep-sea vents use the faint thermal radiation from the hot vent fluids. This produces very little energy, but it demonstrates that photosynthesis isn't absolutely dependent on sunlight. An alien world with extensive hydrothermal activity might develop photosynthetic life that uses volcanic light, living in eternal darkness sustained by geothermal rather than solar energy. Bioluminescence-powered photosynthesis could create bizarre ecological cycles where organisms generate light through chemical reactions, other organisms use that light for photosynthesis, and the products of photosynthesis support the light-generating organisms. This would be less efficient than using a star's light directly. But on a rogue planet drifting through interstellar space with no star, such a system might be the only way photosynthesis could exist at all. The efficiency of photosynthesis varies greatly on Earth, with most plants converting only 1 to 2% of incoming light energy into chemical energy stored in sugars. This low efficiency reflects various constraints and trade-offs in the photosynthetic machinery. Alien photosynthesis might achieve higher efficiency through different molecular mechanisms, different pigment arrangements, or different metabolic pathways. Alternatively, on worlds where light is extremely dim, even 1 or 2% efficiency might be insufficient, driving evolution toward photosynthetic systems that capture and convert light more effectively, perhaps achieving 5 or 10% efficiency through molecular innovations not present on Earth. Timescales of photosynthesis might differ on other worlds. Earth's photosynthesis operates on timescales of milliseconds to seconds for individual reactions, constrained by the speed of enzyme reactions at Earth's temperatures. On a very cold world, reaction rates would be much slower. Photosynthesis might take minutes or hours for reactions that complete in seconds on Earth. This would mean slower growth rates and organisms that live life in slow motion from our perspective. On a hot world, reactions might proceed faster, allowing rapid photosynthesis and potentially faster growth, though this would also require dealing with the instability of biological molecules at high temperatures. The evolution of photosynthesis on Earth took hundreds of millions of years, with simpler forms appearing first and the complex, oxygen-producing photosynthesis we see in plants evolving later. On alien worlds, the evolutionary trajectory might differ. Perhaps photosynthesis evolves quickly, becoming established within the first billion years of life's appearance. Or perhaps it never evolves at all, with life remaining dependent on chemical energy from geological processes rather than light energy. Photosynthesis, while extremely useful, is not inevitable. It requires specific evolutionary innovations, including light-sensitive pigments, electron transport machinery, and carbon-fixing enzymes. A planet might have abundant life that never discovers photosynthesis, remaining microbial and chemosynthetic indefinitely. The seasonal variations on alien worlds would influence photosynthetic strategies. A planet with extreme axial tilt might experience dramatic seasonal variations in light availability, requiring photosynthetic organisms to either hibernate during dark seasons, store energy during bright seasons, or maintain alternative metabolic modes that don't require light. A tidally locked planet with one side permanently facing its star would have a permanent light side and permanent dark side, with photosynthesis possible only on the lit hemisphere or in the twilight zone between light and dark. The atmospheric chemistry would affect what wavelengths reach the surface. Earth's ozone layer absorbs harmful ultraviolet light, preventing it from reaching the surface. A planet without an ozone layer would expose surface organisms to intense UV, requiring either UV protective mechanisms or restriction of photosynthetic life to water, which naturally blocks UV. A planet with a different atmospheric composition, perhaps with sulfur compounds, nitrogen oxides, or exotic hazes, would filter light differently, creating different wavelengths available at the surface, and thus different optimal pigments for photosynthesis. How extraterrestrial plants could photosynthesize encompasses a vast range of possibilities shaped by stellar spectra, atmospheric filtering, available chemistry, and evolutionary contingency. From black plants absorbing every photon under dim red suns to colourful organisms reflecting abundant high-energy light under bright blue stars, from water-splitting oxygen producers to hydrogen sulfide users releasing sulfur, from rapid tropical growth to slow cold world metabolism. Alien photosynthesis would adapt to each world's unique conditions while performing the same basic function, capturing light energy and converting it into chemical energy that powers ecosystems, potentially creating oxygen-rich atmospheres, modifying planetary chemistry in detectable ways, and revealing through their presence that life has discovered on distant worlds what it discovered on Earth. That starlight, properly harnessed through molecular machinery shaped by billions of years of evolution, can power the chemical reactions that sustain living things, turning distant stars into energy sources for biology across the galaxy. How life could survive on rogue planets. Most planets orbit stars, bathed in starlight that provides warmth and energy for any life that might evolve. But scattered throughout the galaxy are worlds that wander alone through the darkness of interstellar space. Rogue planets, ejected from their birth solar systems through gravitational interactions, or perhaps forming in isolation, drifting for billions of years without a sun to orbit. These orphaned worlds seem like the least hospitable places imaginable for life. Cut off from starlight, they receive no external heat source, no energy for photosynthesis, no warming to maintain liquid water on their surfaces. Yet despite these apparently insurmountable obstacles, life might still find ways to survive on rogue planets, drawing on internal heat sources, subsurface environments, and the remarkable adaptability that evolution has demonstrated countless times on Earth when organisms colonize seemingly impossible habitats. The key to habitability on rogue planets is internal heat. Unlike stars, which generate heat through nuclear fusion, rogue planets must rely on residual heat from formation and ongoing heat from radioactive decay of elements in their interiors. When planets form, the process of accretion, countless collisions between smaller bodies that gradually build up the planet, converts kinetic energy into heat. Additionally, gravitational compression, as material piles up, releases energy that heats the planet's interior. A newly formed planet is molten or partially molten, taking millions to billions of years to cool. This primordial heat, combined with heat from radioactive decay of uranium, thorium, potassium, and other radioactive isotopes in the planet's rocks, keeps planetary interiors warm for billions of years. Earth itself generates about 47 terawatts of internal heat, roughly equal to 10,000 large power plants operating continuously. Most of this heat comes from radioactive decay, with some contribution from residual primordial heat and from crystallization of Earth's molten iron core. This internal heat drives plate tectonics, powers volcanic activity, and maintains Earth's magnetic field. A rogue planet of similar size and composition would generate similar amounts of internal heat, regardless of whether it orbits a star or drifts through interstellar space. The challenge is keeping that heat trapped. Without an atmosphere, heat would radiate directly into space, and the planet's surface would quickly reach temperatures only a few degrees above absolute zero, the background temperature of the universe, about -270 degrees Celsius. But a substantial atmosphere could act as insulation, trapping heat through the greenhouse effect and maintaining warmer temperatures at the surface or in the lower atmosphere, even without any external heat source. A rogue planet with a thick hydrogen atmosphere could potentially maintain surface temperatures warm enough for liquid water through atmospheric pressure and greenhouse warming alone. Hydrogen is the lightest and most abundant element in the universe, and large planets can capture and retain massive hydrogen envelopes during formation. The greenhouse effect from a thick hydrogen atmosphere, combined with internal heat radiating from below, could create a temperature profile that allows liquid water to exist at the surface or at some depth within the atmosphere, where pressure and temperature are both suitable. Computer models suggest that a rogue planet several times Earth's mass, with a hydrogen atmosphere perhaps 100 times more massive than Earth's atmosphere, could maintain surface temperatures above the freezing point of water for billions of years, powered only by internal heat. Such a planet would be entirely dark at the surface, no day or night, just eternal darkness. But it would be warm enough for liquid water, and where there's liquid water and a source of energy, life becomes possible. Life on such a world could not depend on photosynthesis, but that's not necessarily a problem. On Earth, entire ecosystems exist in permanent darkness, sustained by chemosynthetic bacteria that extract energy from chemical reactions rather than sunlight. Deep-sea hydrothermal vents host thriving communities where bacteria oxidize hydrogen, sulfide, methane, or hydrogen, using the chemical energy to build organic molecules from carbon dioxide. These chemosynthetic bacteria form the base of food chains that support tube worms, clams, fish, and crustaceans, all living in absolute darkness, kilometers beneath the ocean surface. A rogue planet with liquid water oceans, maintained by internal heat and atmospheric greenhouse warming, could develop similar chemosynthetic ecosystems. Volcanic activity would vent gases like hydrogen, hydrogen sulfide, methane, and carbon dioxide into the water and atmosphere. Bacteria could evolve to extract energy from these chemicals, building organic molecules that could support more complex organisms. The entire biosphere would operate on chemical energy from the planet's interior rather than solar energy, making the planet's life forms independent of any star. Subsurface oceans represent an even more plausible habitat for life on rogue planets. Many worlds in our solar system likely have liquid water oceans beneath ice shells. Europa, Enceladus, possibly Titan, Ganymede, Callisto, Pluto, and other bodies. These oceans are kept liquid by tidal heating from their parent planets, or by internal radioactive heating. A rogue planet with sufficient internal heat and a thick ice shell could maintain a subsurface ocean indefinitely, with the ice providing insulation that prevents the ocean from freezing while protecting it from the harsh radiation and extreme cold of interstellar space. The ice shell on a rogue planet might be very thick, perhaps tens or hundreds of kilometers, creating an insulating layer that traps internal heat far more effectively than any atmosphere. The ocean beneath this ice would be completely dark, protected from the radiation that fills interstellar space, and stable for billions of years. Temperature would be maintained by heat flowing from the rocky mantle below. Hydrothermal vents on the ocean floor would provide chemicals and energy for chemosynthetic life. Such an ocean might be an ideal habitat, more stable than surface oceans on planets orbiting stars where stellar evolution, asteroid impacts, and climate variations create periodic catastrophes. Life in a subsurface ocean on a rogue planet would never know stars exist. The entire biosphere would be confined to the dark ocean, with the ice ceiling above and rocky floor below defining the limits of the habitable universe. Evolution would never produce eyes sensitive to visible light because no visible light exists. Organisms might instead evolve chemical sensing, pressure sensing, electroreception, or other non-visual senses. Intelligence, if it evolved, would develop without ever seeing stars, planets, or anything beyond the ocean's boundaries. Such a civilization might not even realize that a larger universe exists beyond their world, having no way to detect or observe the space around them through kilometers of ice. Geothermal pockets could create localized habitable zones even on rogue planets without global oceans. Volcanic activity or concentrations of radioactive elements could heat specific regions, melting ice to create underground lakes or pockets of liquid water embedded in ice. These isolated water bodies might be small, perhaps only a few kilometers across, but they could persist for millions of years, long enough for life to evolve and diversify within each pocket. Different pockets might develop different ecosystems in isolation from each other, creating multiple independent evolutionary experiments on a single rogue world. Atmosphere composition would profoundly affect habitability. A rogue planet that retained or captured a hydrogen-helium atmosphere during formation could use that atmosphere's greenhouse effect to maintain warmth. Carbon dioxide, methane, and ammonia are all more effective greenhouse gases than hydrogen and would enhance warming at much lower atmospheric masses. A rogue planet with a thick carbon dioxide atmosphere and substantial internal heat might maintain temperatures warm enough for liquid water with a much thinner atmosphere than a hydrogen-dominated world would need. The size of the rogue planet matters significantly. Larger planets generate more internal heat from radioactive decay simply because they contain more radioactive material. Larger planets can also hold thicker atmospheres through stronger gravity and lose heat more slowly because their surface area to volume ratio is smaller. Heat escapes through the surface, but heat is generated throughout the volume, so larger planets stay warm longer. A rogue super-Earth several times, Earth's mass might remain habitable for far longer than an Earth-mass rogue planet, potentially maintaining surface or subsurface liquid water for tens of billions of years or more. Very small rogue planets, Mars-sized or smaller, would struggle to maintain habitability. They would cool quickly, losing internal heat within a few billion years. Their weak gravity would allow atmospheric escape, making it difficult to maintain the thick atmospheres needed for greenhouse warming. However, even small rogue worlds might maintain subsurface liquid water in deep aquifers or isolated pockets warmed by concentrations of radioactive elements or by residual heat from formation for some period after being ejected from their parent system. The abundance of rogue planets remains uncertain, but some estimates suggest they might outnumber stars. If planets are commonly ejected during the chaotic early phases of planetary system formation, the galaxy might contain billions or even trillions of rogue planets drifting through interstellar space. Most would be cold, dark, and apparently lifeless at their surfaces, but some fraction might maintain subsurface oceans or possess the right combination of size, composition, and atmosphere to support life in hidden biospheres, beneath ice or in dark surface oceans sustained by nothing more than the planet's internal warmth. Detecting life on rogue planets would be extraordinarily challenging. These worlds emit no reflected starlight, making them nearly impossible to detect through traditional astronomical methods. They can only be detected through gravitational microlensing. When a rogue planet passes in front of a distant star from Earth's perspective, its gravity briefly magnifies the star's light, or through direct detection of their infrared emission, the faint heat radiating from their surfaces. Neither method provides information about atmospheres, surface conditions, or potential habitability, let alone biosignatures. Future infrared telescopes might be able to detect the warmest rogue planets and potentially characterize their atmospheres if those atmospheres are thick enough to produce detectable spectral features. Finding methane, carbon dioxide, or other gases in unexpected ratios might hint at biological activity, though distinguishing biological from geological sources would be nearly impossible without additional information. Direct exploration by spacecraft seems impractical, given the vast distances between stars and the difficulty of even locating rogue planets, let alone traveling to them. The evolutionary trajectory of life on rogue planets might differ fundamentally from life on planets orbiting stars. Without the regular day-night cycle that drives circadian rhythms on Earth, organisms would have no reason to evolve timekeeping mechanisms tied to planetary rotation. Without seasons caused by axial tilt and orbital motion, there would be no seasonal cycles, no annual rhythms. Life would exist in an eternal, unchanging environment, at least on timescales shorter than geological epochs, potentially leading to very different evolutionary pressures than life on Earth experiences. The isolation of rogue planets creates another interesting possibility. These worlds might serve as interstellar arcs, carrying life between star systems. If a planet with a biosphere is ejected from its home system, life on that planet doesn't necessarily die. If the planet maintains subsurface oceans, through internal heating, life in those oceans could survive indefinitely, potentially for billions of years, as the planet drifts through the galaxy. Eventually, such a planet might be captured by another star system, or it might pass close to a star that warms the planet temporarily, allowing surface life to revive if it was dormant. This mechanism, planets carrying life between star systems, represents a form of panspermia that could spread life throughout the galaxy. How life could survive on rogue planets demonstrates the resilience and adaptability of biology when provided with even minimal requirements. Liquid water, chemical energy, raw materials, and time. A rogue planet cut off from all starlight, drifting through the darkness of interstellar space for billions of years, seems like an impossible place for life. Yet internal heat and thick atmospheres, or ice shells, could create hidden habitats where chemosynthetic ecosystems thrive in eternal darkness, where evolution operates unconstrained by day-night or seasonal cycles, where intelligent beings might arise never knowing that stars exist, and where life demonstrates its ultimate independence from sunlight, proving that biology requires not a sun to orbit, but merely the right chemical conditions and energy sources, expanding the definition of habitable environments to include not just planets in stellar habitable zones, but potentially countless dark worlds adrift in the spaces between the stars, each one a potential harbour for life in the vast ocean of the galaxy. How stars create light and heat. Every star you see in the night sky is a massive nuclear furnace, a sphere of gas so hot and dense at its core that atoms are torn apart and fused back together in reactions that release staggering amounts of energy. The light that reaches your eyes from even the nearest star beyond our sun has travelled for years through the void of space, carrying energy that was created in the unimaginable heat and pressure at that star's core. Understanding how stars create this light and heat means understanding one of the most fundamental processes in the universe, one that has been lighting the cosmos for billions of years and will continue for billions more. Begin at the heart of a star, the core, where conditions are almost beyond comprehension. In our sun, the temperature at the centre reaches about 27 million degrees Fahrenheit. The pressure is equally extreme, about 250 billion times the atmospheric pressure at Earth's surface. Under these conditions, matter behaves in ways completely unlike anything we experience in daily life. The gas is so hot that atoms cannot exist as atoms. Electrons are stripped away from their nuclei, creating a plasma where negatively charged electrons and positively charged nuclei move independently through a churning, seething mass. At these temperatures and pressures, atomic nuclei that would normally repel each other, they're all positively charged, and like charges repel, move so fast that they occasionally collide with enough energy to overcome this electrical repulsion. When hydrogen nuclei, which are simply protons, collide at these tremendous speeds, they can fuse together. This is nuclear fusion, and it's the source of all the energy a star produces. The most common fusion process in stars like our Sun is called the proton-proton chain. Picture two protons colliding at enormous speed in the star's core. Usually, they just bounce off each other, repelled by their mutual positive charge. But occasionally, very rarely, quantum mechanics allows something remarkable to happen. The two protons fuse, and in that instant, one of them transforms into a neutron through a process involving the weak nuclear force. This creates a nucleus of heavy hydrogen, called deuterium, consisting of one proton and one neutron bound together. This single fusion event releases energy in multiple forms. A positron is ejected, the antimatter counterpart of an electron, A neutrino, an almost massless particle that barely interacts with anything, streams away at the speed of light, and energy is released as gamma-ray radiation, the most energetic form of light. The positron almost immediately encounters a regular electron, and they annihilate each other in a burst of energy. The neutrino escapes the star entirely, passing through all the overlying layers as if they weren't there, reaching space in just a few seconds. But this is only the first step. The deuterium nucleus that formed doesn't last long on its own. It quickly collides with another proton and fuses with it, creating a nucleus of helium-3, which has 2 protons and 1 neutron. This fusion releases more energy, this time in the form of a gamma ray. Finally, 2 helium-3 nuclei collide and fuse, forming ordinary helium-4, which has 2 protons and 2 neutrons, and releasing 2 protons back into the mix to start the process over again. The net result of all these steps is that 4 hydrogen nuclei have been converted into 1 helium nucleus. And here's the crucial part. The helium nucleus weighs slightly less than the 4 hydrogen nuclei that went into making it. About 0.7% of the mass has disappeared. Where did it go? It was converted into energy, according to Einstein's famous equation, E equals mc squared. That tiny fraction of mass, when multiplied by the speed of light squared, represents an enormous amount of energy. In our Sun, this process converts about 600 million tons of hydrogen into helium every single second. About 4 million tons of matter are completely converted into energy each second. This has been happening for about 4.6 billion years, and the Sun has enough hydrogen fuel to continue for another 5 billion years or so before it exhausts the hydrogen in its core. The energy released in these fusion reactions, created at the core of the star, must somehow make its way to the surface, to be radiated into space as light and heat. This journey is neither quick nor straightforward. The gamma rays produced in the core don't simply stream to the surface. The star's interior is incredibly dense, and a gamma ray photon can't travel far before it collides with an electron or an atomic nucleus. When a high-energy gamma-ray photon hits an electron, it typically gets absorbed and then re-emitted, but not necessarily in the same direction, and often at a slightly lower energy. The photon bounces around randomly, absorbed and re-emitted countless times, following what scientists call a random walk. Each interaction changes the photon's direction randomly, so it might move inward toward the core just as often as it moves outward toward the surface. This random walk means that energy takes an extraordinarily long time to travel from the core to the surface. A photon of light can travel from the Sun to Earth, a distance of 93 million miles, in about 8 minutes. But that same photon trying to escape from the Sun's core to its surface, a distance of only about 400,000 miles, takes somewhere between 100,000 and a million years. The exact number is uncertain because the path is so random and complex, involving countless billions of interactions. As the energy works its way outward through this radiative zone, the photons gradually lose energy with each interaction. The high-energy gamma rays from the core become X-rays, then ultraviolet light, then visible light, and eventually include infrared radiation. By the time the energy reaches the outer portions of the star, it has been divided and redistributed among countless photons of various energies. About 2/3 of the way out from the Sun's core, the nature of energy transport changes. The temperature has dropped to the point where atoms can hold onto some of their electrons, and the gas becomes more opaque. In this outer region, called the convection zone, energy is transported primarily by the physical motion of hot gas rather than by radiation. Hot plasma rises toward the surface, cools, and then sinks back down, creating vast circulation cells. Think of a pot of boiling water with bubbles of hot water rising and cooler water sinking, but on a stellar scale where individual convection cells can be larger than Earth. This convection brings hot material from the interior up to the photosphere, the visible surface of the star. Here, finally, energy can escape into space. The photosphere is still incredibly hot by earthly standards, about 10,000 degrees Fahrenheit on the Sun, but it's cool enough that photons can finally stream away into space without being immediately reabsorbed. The light that leaves the photosphere carries information about the star's surface temperature in its colour and spectrum. Hotter stars emit more blue and ultraviolet light, appearing blue or white to our eyes. Cooler stars emit more red and infrared light, appearing orange or red. Our Sun, with a surface temperature around 10,000 degrees, emits most of its energy in the visible part of the spectrum, peaking in the green-yellow range, though it appears white or slightly yellow to our eyes because it emits all colours of visible light. Not all stars use the same fusion process as our Sun. In more massive stars with hotter cores, a different set of reactions called the CNO cycle dominates. This cycle uses carbon, nitrogen, and oxygen nuclei as catalysts to fuse hydrogen into helium. The carbon, nitrogen, and oxygen aren't consumed in the process. They're regenerated at the end of the cycle, but their presence allows the fusion to proceed more rapidly at higher temperatures. Very massive stars can burn through their hydrogen fuel in just a few million years, compared to the Sun's 10 billion year lifetime. The energy output of a star is precisely balanced with its gravity. Gravity tries to compress the star, but the pressure from the hot gas, heated by fusion, pushes outward. These forces are in equilibrium, which is why stars are stable over long periods. If fusion produces too much energy, the star expands and cools slightly, slowing the fusion rate. If fusion slows down, the star contracts and heats up, increasing the fusion rate. This self-regulating mechanism keeps stars stable. The heat generated in a star's core doesn't just produce light, it creates the pressure that holds the star up against its own gravity. Without fusion, a star would collapse under its own weight. This is what happens when a star runs out of fuel. The fusion stops, the pressure drops, and gravity takes over, leading to dramatic events like supernova explosions or the formation of dense stellar remnants. Different layers of the star have vastly different temperatures. The core, where fusion occurs, is the hottest. The temperature decreases as you move outward through the radiative zone and convection zone. The photosphere, the visible surface, is the coolest part of the star proper, though above it lies the chromosphere and corona, regions of the star's atmosphere that are paradoxically hotter than the surface, heated by magnetic fields and shock waves rather than by radiation from below. The amount of energy a star produces is staggering. Our Sun outputs about 386 billion megawatts of power every second. That's more energy than humanity has used in its entire history, released every single second. And the Sun is actually a fairly average, middle-sized star. Some massive stars output 1 million times more energy than the Sun, burning so bright and hot that they exhaust their fuel and die in just a few million years. Every photon of sunlight that warms your face, every ray that allows plants to photosynthesize and create the oxygen you breathe, every bit of light that illuminates the day, began as a fusion reaction in the Sun's core. The energy in that light was created when hydrogen nuclei overcame their electrical repulsion and fused into helium, converting a tiny amount of mass into energy. That energy then spent hundreds of thousands of years bouncing randomly through the Sun's interior before finally reaching the surface and streaming across space to Earth. This process of creating light and heat through nuclear fusion is happening right now in hundreds of billions of stars in our galaxy alone, and in countless more stars throughout the universe. It's been happening since the first stars formed a few 100 million years after the Big Bang, and it will continue for trillions of years into the future, until the last stars finally exhaust their fuel and fade away, leaving the universe dark and cold. But for now, and for the foreseeable future, the universe is filled with light and heat, gifts of the fusion fires burning in the hearts of stars. How the moon pulls on Earth's oceans. Twice each day, the ocean rises up beaches and coastlines around the world, then retreats back toward the sea. This rhythmic rise and fall of the tides has shaped human civilization for thousands of years, governing when ships could enter harbours, when fishermen could gather shellfish from tidal pools, and when coastal communities needed to prepare for high water. The connection between these tides and the moon was recognised in ancient times, but understanding exactly how the moon creates tides requires thinking carefully about gravity, how it varies with distance, and how Earth's ocean responds to forces that stretch and squeeze it in complex ways. The fundamental cause of tides is gravity, but not gravity in the simple sense of the moon pulling water toward itself. If that were the entire story, we would see one bulge of water on the side of Earth facing the moon, and that would be the end of it. Instead, we observe two tidal bulges, one on the side facing the moon and another on the opposite side of Earth. This puzzling fact confused natural philosophers for centuries, until Isaac Newton, in his Principia Mathematica, published in 1687, provided the correct explanation using his law of universal gravitation and his laws of motion. The key insight is that the moon's gravity pulls on every part of Earth, but it pulls with different strengths depending on distance. The side of Earth closest to the moon experiences stronger gravitational attraction than Earth's centre, which in turn experiences stronger attraction than the far side. This difference in gravitational force across Earth's diameter creates what are called tidal forces, forces that try to stretch Earth along the line, connecting it to the moon, while simultaneously squeezing it perpendicular to that line. Imagine Earth's structure for a moment. The solid rock of Earth's crust and mantle resists deformation quite strongly. While tidal forces do deform the solid Earth slightly, raising and lowering the ground by about a foot, the effect is not dramatic because rock is stiff and strong. The oceans, however, are fluid. They can flow freely in response to forces, and they respond readily to the tidal forces that the solid Earth largely resists. Consider a point on Earth's surface directly beneath the moon. The water at this location is about 4,000 miles closer to the moon than Earth's centre. The moon's gravitational pull weakens with distance according to an inverse square law. Double the distance and the force becomes 1/4 as strong. This means the ocean on the near side experiences a gravitational pull toward the moon that's about 7% stronger than the pull experienced by Earth's centre. This differential force pulls the ocean away from Earth's centre, creating a bulge of water on the moon-facing side. Now consider the opposite side of Earth, the point farthest from the moon. Here the ocean is about 4,000 miles farther from the moon than Earth's centre. The gravitational pull from the moon at this location is about 7% weaker than at Earth's centre. Earth's centre is being pulled toward the moon more strongly than the water on the far side, effectively pulling Earth away from the water and leaving the water behind. The result is another bulge on the side opposite the moon. This creates the characteristic two-bulge pattern. If you could freeze time and look at Earth from space, you would see the oceans slightly elongated along the Earth-Moon line, with high water on both the near and far sides and low water at the points 90 degrees away from the moon. As Earth rotates beneath these bulges, any given point on Earth's surface passes through 2 high tides and 2 low tides each day, though not exactly every 12 hours, because the moon is also moving in its orbit, shifting the position of the bulges over time. The height of these tidal bulges would be quite modest if they responded only to the moon's gravitational pull, perhaps a foot or 2 in the open ocean. But the actual tides we observe at coastlines can be dozens of feet high. This amplification occurs because of the way ocean basins are shaped and because of resonance effects as water sloshes back and forth in confined spaces. The Bay of Fundy in Canada experiences the world's highest tides, sometimes exceeding 50 feet, because the bay's shape and size create a natural resonance that amplifies the tidal forcing from the moon and sun. The sun also creates tides on Earth, though they're smaller than lunar tides despite the Sun's vastly greater mass. The reason is distance. The Sun is about 400 times farther from Earth than the Moon, and tidal forces depend not just on mass, but on how much the gravitational pull varies across Earth's diameter. The Sun's great distance means its gravitational pull varies less across Earth than the Moon's does, making solar tides about 46% as strong as lunar tides, a ratio that Pierre-Simon Laplace calculated in detail in his comprehensive work on celestial mechanics in the late 1700s. The interaction between solar and lunar tides creates the familiar spring and neap tide cycle. When the Moon and Sun align, either on the same side of Earth during a new moon or on opposite sides during a full moon, their tidal effects add together, creating spring tides with especially high tides and especially low tides. The name has nothing to do with the season, but comes from the idea that the tides spring forth. When the Moon and Sun are at right angles as seen from Earth during first and third quarter moons, their tidal effects partially cancel, creating neap tides with smaller tidal ranges. This 2-week cycle of spring and neap tides is predictable and was well understood by ancient mariners, though they lacked Newton's gravitational explanation for why it occurred. The timing of tides is not as simple as one might expect. If you observe the tides at any coastal location, you'll notice that high tide doesn't occur exactly when the Moon is overhead or exactly when it's on the opposite side of Earth. There's typically a delay of several hours called the tidal lag. This occurs because the ocean cannot respond instantaneously to the changing tidal forces. Water has inertia, it takes time to accelerate and decelerate, and friction between the moving water and the ocean floor dissipates energy, creating phase lags between the tidal forces and the ocean's response. These friction effects have profound long-term consequences. As tidal bulges try to follow the Moon, but are dragged forward slightly by Earth's rotation, they create a gravitational pull on the Moon that's not perfectly aligned with the Earth-Moon line. This misaligned pull acts to accelerate the Moon in its orbit, gradually increasing its orbital energy and causing it to move away from Earth. Precise laser ranging measurements using reflectors left on the Moon by Apollo astronauts have confirmed that the Moon is receding from Earth at about 1.5 inches per year. This recession cannot continue indefinitely at the current rate. As the Moon moves farther away, tidal effects weaken, slowing the recession. But over the 4.5 billion years since the Moon formed, likely from debris created when a Mars-sized object collided with the young Earth, the Moon has moved substantially farther from Earth. Early in Earth's history, when the Moon was much closer, perhaps only 15,000 miles away compared to today's 240,000 miles, tidal forces were enormously stronger. Tides might have been hundreds of feet high, and the Moon would have appeared many times larger in the sky, looming over the horizon like an enormous sphere dominating the heavens. The energy dissipated by tidal friction doesn't just affect the Moon's orbit, it also affects Earth's rotation. The gravitational drag from the tidal bulges acts to slow Earth's rotation gradually. Each century, Earth's day lengthens by about 1.7 milliseconds. This seems negligible, but over geological time, it accumulates. Fossil evidence from ancient corals, which show daily growth bands much like tree rings, indicates that 400 million years ago, Earth's day was only about 22 hours long, and a year contained about 400 days. The Moon was closer, Earth rotated faster, and tides were stronger. This tidal interaction between Earth and the Moon is an example of tidal locking in progress. The Moon is already tidally locked to Earth, always showing the same face toward Earth because tidal forces from Earth have synchronized the Moon's rotation period with its orbital period. Earth is gradually becoming tidally locked to the Moon as well, though this process will take tens of billions of years to complete, longer than the remaining lifetime of the Sun. If it could be completed eventually, Earth would always show the same face to the moon, and the moon would hang stationary in the sky over one hemisphere, never visible from the other. Other bodies in the solar system experience even more extreme tidal effects. Jupiter's moon, Io, the most volcanically active body in the solar system, is heated internally by tidal flexing. As Io orbits Jupiter in an elliptical path, the tidal forces it experiences vary in strength, squeezing and stretching the moon's interior. This constant kneading generates tremendous heat through friction, keeping Io's interior molten and driving its spectacular volcanic eruptions. This process, predicted by Stanton Peele and colleagues just before the Voyager spacecraft discovered Io's volcanism in 1979, is called tidal heating. Saturn's moon Enceladus experiences similar tidal heating, though less extreme than Io. The heat from tidal flexing keeps a subsurface ocean liquid beneath Enceladus's icy crust, and tidal stresses crack the ice at the South Pole, allowing geysers of water to erupt into space. Europa, another moon of Jupiter, likely has its subsurface ocean maintained by tidal heating as well, making it one of the most promising places to search for life beyond Earth. Tidal forces can also be destructive. Every large body creates a tidal limit, called the Roche limit, after Edouard Roche, who calculated it in 1848, inside which tidal forces exceed the self-gravity holding a satellite together. A moon that wanders inside the Roche limit will be torn apart by tidal forces, pulled into fragments that spread into a ring around the planet. Saturn's magnificent ring system may have originated this way, from a moon that either formed inside the Roche limit or migrated inward and was disrupted. Tidal forces operate throughout the universe. Binary stars experience tides that can transfer mass from one star to its companion. Black holes create tidal forces so extreme that they can tear apart stars that pass too close, creating spectacular tidal disruption events. Galaxies passing near each other experience tidal forces that stretch them into long streams of stars, creating the tidal tails visible in many interacting galaxies. The same physics that causes ocean tides on Earth, the differential pull of gravity across an extended object, operates on scales from moons and planets to stars and galaxies. The tides we observe at the beach are the local manifestation of a cosmic dance between Earth and Moon, a gravitational interaction that has been occurring since the Moon formed and will continue for billions of years into the future. Every incoming wave, every tide pool exposed at low tide, every ship waiting for high water to enter harbour is part of this larger story of how gravity shapes the motion of celestial bodies and how the Moon, our constant companion in the night sky, continues to sculpt the behaviour of Earth's oceans through the subtle but inexorable pull of tidal forces. The biosignatures that reveal living planets. Detecting life on distant planets represents one of the greatest challenges in astronomy. We cannot visit these worlds, cannot scoop up soil samples, cannot peer through microscopes at alien microbes. Most exoplanets appear as nothing more than tiny dips in their star's brightness as they transit, or slight wobbles in the star's position, caused by the planet's gravitational pull. Yet from these minimal observations, measurements of light passing through a planet's atmosphere during transit, analysis of the planet's reflected light, characterization of its temperature and size, astronomers hope to determine whether life exists on worlds many light-years away. The key lies in biosignatures, detectable signs that life is present, chemical or physical features that cannot easily be explained by non-biological processes, and that point toward the presence of living organisms modifying their planet's environment in measurable ways. Oxygen stands as the most famous biosignature, the gas that astronomers most eagerly search for in exoplanet atmospheres. On Earth, oxygen makes up 21% of the atmosphere, a concentration vastly higher than would exist without life. Oxygen is highly reactive. It combines readily with rocks, organic molecules, and other materials, removing oxygen from the atmosphere unless something continually replenishes it. On Earth, that something is photosynthetic life. Plants, algae, and photosynthetic bacteria use sunlight to split water molecules, releasing oxygen as a waste product. Without this biological production, Earth's atmospheric oxygen would disappear within a few million years as it reacted with surface materials. Detecting oxygen in an exoplanet's atmosphere would strongly suggest the presence of photosynthetic life, though not definitively. Oxygen can be produced through non-biological processes. Photodissociation of water vapor by ultraviolet light, for instance, can split water molecules and release oxygen. But these abiotic processes typically produce only small amounts of oxygen compared to the abundant oxygen that photosynthesis generates. A planet with significant oxygen in its atmosphere, particularly if that oxygen persists over long periods, would be a compelling candidate for hosting life. However, oxygen alone doesn't guarantee life, and the absence of oxygen doesn't rule out life. Earth's atmosphere contained very little free oxygen for the first 2 billion years or more of life's existence. Early life consisted entirely of anaerobic organisms that didn't produce oxygen. Even after photosynthesis evolved, it took hundreds of millions of years for oxygen to accumulate in the atmosphere, because the gas initially reacted with dissolved iron in the oceans and with rocks before building up in the air. An alien planet might be teeming with life, yet have no oxygen signature if that life hasn't evolved oxygenic photosynthesis, or if oxygen-producing organisms haven't yet generated enough oxygen to overwhelm the chemical sinks that remove it. Methane represents another important biosignature, particularly in combination with oxygen. Methane and oxygen react with each other readily. In the presence of oxygen, methane breaks down relatively quickly through oxidation. For both gases to coexist in significant quantities in an atmosphere, something must be continually producing them faster than they react and disappear. On Earth, biological processes produce both gases. Photosynthesis produces oxygen, while certain bacteria called methanogens produce methane as a metabolic waste product. The simultaneous presence of both gases in substantial concentrations would be difficult to explain through non-biological chemistry alone. Methane itself can be produced abiotically through geological processes. Volcanic activity, hydrothermal systems, and reactions between water and certain rocks can all generate methane without life. But these sources typically produce methane at lower, steadier rates than biological sources. If observations show variable methane levels, perhaps seasonal variations suggesting biological activity that waxes and wanes with seasons, or if methane concentrations are higher than geological sources could explain, this would strengthen the case for biology. Phosphine burst into the biosignature conversation in 2020 when scientists reported detecting this gas in Venus's atmosphere. Phosphine consists of one phosphorus atom bonded to 3 hydrogen atoms, and on Earth it's primarily produced by anaerobic bacteria living in oxygen-free environments. Phosphine is quickly destroyed by ultraviolet light and chemical reactions, so detecting it in an atmosphere suggests something must be continuously producing it. The Venus detection remains controversial. Subsequent observations haven't definitively confirmed the phosphine signal, and some scientists argue that non-biological chemistry could produce phosphine in Venus's harsh environment. But the episode highlighted phosphine as a potential biosignature worth searching for, particularly on worlds very different from Earth. Ozone, a molecule consisting of 3 oxygen atoms, serves as a secondary oxygen biosignature. Ozone forms in atmospheres when ultraviolet light breaks apart molecular oxygen, and the freed oxygen atoms recombine into ozone molecules. Ozone is easier to detect spectroscopically than molecular oxygen, So finding ozone in an exoplanet's atmosphere provides strong evidence that molecular oxygen is also present, which in turn suggests photosynthetic life. Ozone also absorbs harmful ultraviolet radiation, protecting planetary surfaces from DNA-damaging rays. The presence of an ozone layer suggests not only that photosynthetic life produces oxygen, but also that conditions at the surface might be suitable for more complex life that would otherwise be sterilized by ultraviolet radiation. Nitrous oxide, laughing gas, represents another possible biosignature. On Earth, certain bacteria produce nitrous oxide as a byproduct of nitrogen metabolism. Like oxygen and methane, nitrous oxide is reactive and doesn't persist indefinitely in atmospheres without continuous production. Detecting significant amounts of nitrous oxide, particularly in combination with other biosignature gases, would strengthen the case for biological activity. However, nitrous oxide can also be produced abiotically through lightning, volcanic activity, and chemical reactions in the atmosphere, so its detection alone wouldn't be definitive. Sulfur compounds offer additional biosignature possibilities. Dimethyl sulfide, produced by marine phytoplankton on Earth, has a distinctive spectral signature. Hydrogen sulfide, while toxic to most Earth life, is produced by certain bacteria and might be an important gas in alien biospheres based on sulfur chemistry rather than oxygen. Carbonyl sulfide, though produced both biologically and geologically, might still serve as a biosignature when detected in combination with other gases in ways that geological processes can't easily explain. The key to biosignature detection often lies not in finding a single gas, but in detecting combinations of gases that shouldn't coexist in equilibrium. Chemical disequilibrium, the simultaneous presence of gases that react with each other, suggests that something is continually producing those gases, driving the atmosphere away from chemical equilibrium. Life is inherently a disequilibrium phenomenon. Living organisms take in certain chemicals and energy, use them to maintain organization, and grow and excrete different chemicals as waste. This metabolism creates chemical imbalances that wouldn't exist in a sterile abiotic system at equilibrium. Earth's atmosphere is far from chemical equilibrium precisely because life constantly produces gases that react with each other and with the environment. An alien planet with life would similarly maintain chemical disequilibrium, though the specific gases involved might differ completely from Earth. The challenge lies in distinguishing biological disequilibrium from geological or atmospheric processes that can also create unusual gas combinations. Temporal variations in biosignatures provide additional evidence. Seasonal changes in atmospheric composition might reflect biological cycles, plant growth during spring and summer, dormancy during fall and winter. Daily variations might reflect photosynthesis, starting at dawn and stopping at night. Finding these rhythmic patterns would be strong evidence for biology, because non-biological processes rarely produce such regular, predictable cycles tied to light and seasons. Surface features offer another category of biosignatures. On Earth, large-scale biological activity affects the planet's appearance in ways that might be detectable from space. Vegetation reflects light in characteristic ways. The red edge, where plant reflectance increases sharply between red and near-infrared wavelengths, as plants reflect infrared light they cannot use for photosynthesis. This vegetation signature is quite distinctive and might be detectable on exoplanets if vegetation covers substantial portions of the surface. However, alien photosynthetic organisms might not have a red edge. Plants on a planet orbiting a red dwarf star might be black to maximize absorption of the dim red light available, or they might be other colors, entirely depending on their star's spectrum and their photosynthetic pigments. Large-scale color changes across seasons could indicate biological activity. If part of a planet's surface changes color seasonally, perhaps from green to brown, as vegetation grows, and then senesces, this would be difficult to explain through geology alone. Detecting such changes would require extremely high-resolution observations across multiple seasons, pushing the limits of even the most advanced telescopes. But future extremely large telescopes might achieve this capability for the nearest exoplanets. Ocean glint patterns might reveal biological activity in oceans. Certain types of marine life produce compounds that affect water's surface tension or create surface films that change how light reflects off the ocean. These effects, though subtle, create characteristic glint patterns that differ from pure water. Detecting such patterns from light years away would be extraordinarily challenging, but might become possible with next-generation direct imaging telescopes. Atmospheric hazes created by biological activity represent another potential signature. On Earth, isoprene and other organic compounds released by plants contribute to atmospheric haze. On Titan, Saturn's moon, photochemistry creates organic hazes that give the atmosphere its orange color. Distinguishing biological from non-biological hazes would be difficult, but characteristic compositions or variations might provide clues. A planet with organic hazes that change seasonally, for instance, might have biological sources for those hazes. Artificial light on the night side of a planet would be an unambiguous technosignature, a sign not just of life, but of technological civilization. Earth's night side is bright with city lights, electricity use, and various artificial illumination. An alien civilization would likely develop artificial lighting at some stage of technological development, and if they use inefficient lighting that wastes energy by sending light upward into space, rather than directing it all downward toward the ground, their cities might be detectable. However, detecting such faint light from an exoplanet would require extraordinary capabilities beyond current technology, though future direct imaging telescopes might achieve this for the nearest, potentially inhabited worlds. Industrial pollution offers another technological biosignature. Chlorofluorocarbons, CFCs, are entirely artificial. They don't exist naturally and are produced only through industrial chemistry. Detecting CFCs in an exoplanet's atmosphere would be definitive evidence of technological civilization. Other industrial pollutants, nitrogen dioxide from combustion, sulfur dioxide from industry, certain combinations of gases that indicate smelting or chemical manufacturing, might also be detectable. However, some of these gases also have natural sources from volcanoes or other geological processes, so detecting them in amounts far exceeding natural production rates would be necessary to infer industrial activity. The challenge of false positives, non-biological processes that mimic biosignatures, looms large in biosignature detection. Every proposed biosignature has at least some possible abiotic production mechanism. Oxygen can come from water photodissociation. Methane can come from geology. Phosphine might be produced by unknown atmospheric chemistry. Distinguishing true biosignatures from false positives requires careful analysis of gas abundances, combinations, variations over time, and compatibility with the planet's other known properties. Context matters enormously. Finding oxygen in the atmosphere of a planet with a surface temperature of 500 degrees would not suggest life. The planet is too hot for liquid water and likely for any chemistry we would recognize as living. Finding oxygen on a planet in the habitable zone with liquid water on its surface would be far more compelling. Finding oxygen along with methane, nitrous oxide, and seasonal variations in atmospheric composition on such a planet would be extraordinarily difficult to explain without biology. The search for biosignatures requires sophisticated instruments that can analyze light passing through exoplanet atmospheres during transit. As a planet passes in front of its star, some starlight passes through the planet's atmosphere, and gases in that atmosphere absorb light at specific wavelengths, creating an absorption spectrum. By comparing the star's spectrum with and without the planet in front of it, astronomers can determine which wavelengths are absorbed and thus which gases are present in the atmosphere. The James Webb Space Telescope, launched in 2021, has the sensitivity to detect biosignature gases in the atmospheres of certain types of exoplanets, particularly those orbiting small dim red dwarf stars, where the ratio of planet atmosphere to star is more favourable. Future missions propose space telescopes like the Habitable Worlds Observatory or ground-based extremely large telescopes currently under construction will have even greater capabilities, potentially able to characterize Earth-sized planets in the habitable zones of sun-like stars, the most promising targets for finding life as we know it. These missions might detect multiple biosignature gases simultaneously, observe seasonal and diurnal variations, and potentially even directly image planets and analyze their surface properties. The biosignatures that reveal living planets encompass atmospheric gases that shouldn't coexist, chemical disequilibrium maintained by constant biological production, temporal variations that reflect biological cycles, surface properties that change with seasons, and for technological life, pollution, artificial lighting, and deliberate signals broadcast into space. Each signature provides a puzzle piece, and no single piece definitively proves life. But multiple signatures detected together, in combinations difficult to explain through non-biological processes, could provide compelling evidence that we've detected life beyond Earth, transforming the ancient question of whether we're alone from philosophy into science, revealing that the universe contains not just planets and stars, but living worlds where chemistry has crossed the threshold into biology, where organisms grow and reproduce and evolve, where perhaps intelligence has emerged to contemplate its own existence and wonder, as we do, whether anyone else is out there among the countless worlds orbiting distant stars. How we measure the weight of space objects. When astronomers announce that Jupiter has more than 300 times Earth's mass, or that a distant black hole contains several billion times the Sun's mass, these numbers might seem impossibly precise. How can we possibly weigh objects millions or billions of miles away, objects we can never visit or touch, objects that are sometimes completely invisible? The answer lies not in direct measurement, but in observing how these objects interact gravitationally with their surroundings. Mass reveals itself through gravity, and by watching how objects move under gravitational influence, astronomers can calculate masses with remarkable accuracy using principles that Isaac Newton worked out more than 300 years ago. The fundamental principle is simple. The more massive an object is, the stronger its gravitational pull, and the faster other objects must move to orbit it. This relationship, encoded in Newton's law of universal gravitation and his laws of motion, allows us to determine mass from orbital motion. If you know how fast something orbits and how far away it is from the object it's orbiting, you can calculate the central object's mass. For planets in our solar system, we measure their masses by observing their moons. Jupiter has dozens of moons, and each one's orbital period and distance from Jupiter reveals Jupiter's mass. The formula is straightforward in principle. The orbital period squared is proportional to the orbital distance cubed divided by the central mass. By measuring the period and distance, we can solve for the mass. The more massive the central object, the faster moons must orbit at a given distance to avoid falling inward. Jupiter's moon Io orbits very close to Jupiter and completes an orbit in only about 42 hours. Because Jupiter's immense mass creates powerful gravity, our moon takes 27 days to orbit Earth at a similar distance because Earth is much less massive than Jupiter. For planets without moons, Mercury and Venus, determining mass required more ingenuity. Before the space age, astronomers studied how these planets affected each other's orbits through their gravitational interactions. When two planets pass relatively close to each other, their gravitational pulls slightly deflect each other's paths. By precisely measuring these tiny perturbations over years of observations, astronomers could infer the masses of the planets involved. Space probes visiting these planets provided much more accurate mass measurements by observing how the planet's gravity affected the spacecraft trajectories. Measuring Earth's mass required understanding gravity itself. In the late 18th century, British scientist Henry Cavendish performed a delicate experiment using a torsion balance, a horizontal bar suspended by a thin wire with lead spheres at each end. By bringing large lead masses near the suspended spheres and measuring like the tiny twist in the wire caused by gravitational attraction, Cavendish determined the strength of gravity between known masses. This measurement, combined with the known acceleration of gravity at Earth's surface, allowed calculation of Earth's mass. The experiment is sometimes described as weighing the Earth, though it really measured how strongly Earth's gravity pulls compared to the gravity between laboratory masses. For the Sun, measuring mass is straightforward because Earth and all other planets orbit it. Earth orbits the Sun at a distance of about 150 million kilometers with an orbital period of 1 year. Plugging these numbers into the orbital equation gives the Sun's mass about 2 × 10 to the 30th power kilograms, or about 330,000 times Earth's mass. The exact same calculation works for any star with planets. Measure the planet's orbital distance and period, and you can determine the star's mass. Binary star systems, 2 stars orbiting each other, provide mass measurements for individual stars. By watching the stars orbit their common center of mass and measuring their orbital periods, distances and velocities, astronomers can determine both stars' masses separately. This technique has measured thousands of stellar masses, revealing the relationship between a star's mass and its other properties like luminosity and temperature. These measurements show that stars range from about 8% of the Sun's mass for the smallest red dwarfs up to perhaps 150 times the Sun's mass for the most massive stars. For more distant objects, techniques become more sophisticated but still rely on gravitational effects. Galaxies contain hundreds of billions of stars, and measuring a galaxy's mass means measuring how fast stars and gas orbit within it. By observing the rotation speeds at different distances from the galactic center and applying the same orbital principles, astronomers can calculate the total mass enclosed within each radius. This technique revealed the existence of dark matter. The rotation speeds in the outer parts of galaxies are far too high to be explained by the visible stars and gas alone, requiring the presence of large amounts of invisible mass. Galaxy clusters, groups of hundreds or thousands of galaxies, have their masses measured through multiple techniques. One method observes the motions of individual galaxies within the cluster. The galaxies orbit within the cluster's gravitational potential, and their velocities reveal the cluster's total mass. Another technique uses gravitational lensing, the bending of light from more distant galaxies by the cluster's gravity. The amount of bending depends on the cluster's mass, so by measuring how background galaxies appear distorted, astronomers can map the cluster's mass distribution, including dark matter. Black holes present special challenges because they are invisible and often have no nearby objects in simple orbits. For stellar mass black holes in binary systems, astronomers measure the orbital motion of the visible companion star. The star's velocity and orbital period reveal the black hole's mass, even though the black hole itself emits no light. This technique confirmed that several X-ray binary systems contain objects too massive to be neutron stars. They must be black holes. Supermassive black holes at galaxy centers are weighed by observing stars or gas orbiting near them. The Milky Way's central black hole, Sagittarius A star, has its mass measured precisely by tracking individual stars as they orbit. One star, designated S2, completes an orbit every 16 years in an elongated ellipse that brings it within about 120 times Earth's distance from the Sun, extremely close by galactic standards. By measuring S2's position and velocity throughout its orbit, astronomers calculated the black hole's mass at about 4 million times the Sun's mass. This measurement is accurate to within a few percent, despite the black hole being 26,000 light-years away. More distant supermassive black holes are measured through the motion of stars or gas closer to the black hole than telescopes can individually resolve. Instead, spectroscopy measures the range of velocities present in the light coming from the galaxy's central region. Broader velocity distributions indicate faster-moving material, which requires more mass to keep the material bound. Using this technique, astronomers have measured black hole masses ranging from millions to billions of solar masses in galaxies across the universe. Gravitational waves from merging black holes provide another mass measurement technique. When two black holes spiral together and merge, they emit gravitational waves, ripples in space-time itself, detected by observatories like LIGO. The frequency and amplitude of these waves encode information about the black hole's masses. The first gravitational wave detection in 2015 came from two black holes weighing about 29 and 36 solar masses that merged into a single black hole of about 62 solar masses, with 3 solar masses worth of energy radiated away as gravitational waves during the collision. For objects we can visit with spacecraft, mass measurements become more direct. The spacecraft's trajectory bends as it passes the object, with the deflection determined by the object's mass. By tracking the spacecraft's position using radio signals and measuring the Doppler shift in those signals, mission controllers determine the trajectory precisely. Comparing the observed trajectory to computer models reveals the mass that must have caused that particular deflection. This technique has measured masses of asteroids, comets, and moons with no satellites of their own. Small asteroids present particular challenges. Without satellites, and too small to significantly affect spacecraft at typical flyby distances, their masses remained uncertain until spacecraft flew very close or even orbited them. The near-Shoemaker spacecraft orbited asteroid Eros for a year, precisely measuring Eros's mass and density. The Hayabusa and OSIRIS-REx missions orbited small asteroids, Ryugu and Bennu respectively, measuring their masses through orbital mechanics and revealing that both asteroids are loose rubble piles rather than solid rocks. The precision of mass measurements varies enormously. The Sun's mass is known to about 7 significant figures. Earth's mass is known even more precisely because we can measure Earth's gravitational field from satellites in low orbit. Jupiter's mass is known very precisely from spacecraft tracking, but the mass of a distant galaxy might be uncertain by 10 or 20%, and masses of galaxy clusters can be uncertain by even more, particularly if dark matter doesn't follow the same distribution as visible matter. Understanding the limitations matters. When astronomers quote a mass, there's always uncertainty attached. Reporting that a black hole contains about 4 million solar masses acknowledges this uncertainty. The actual value might be 3.8 million or 4.2 million, and that range represents our measurement precision, not variability in the black hole's mass. All these techniques ultimately trace back to gravity, the fundamental force that governs how massive objects interact across space. Mass creates gravity, gravity creates motion, and by observing that motion precisely, we can work backward to determine the mass that caused it. From moons orbiting planets, to galaxies orbiting within clusters, from binary stars wheeling around each other, to stars orbiting supermassive black holes, the cosmos is filled with objects whose motions reveal the masses of the bodies that control them. By watching these cosmic dances and applying the mathematical laws that Newton first articulated, astronomers can weigh objects from the smallest asteroids to the largest galaxy clusters, measuring masses across a range spanning more than 20 orders of magnitude. From asteroids weighing billions of tons to galaxy clusters weighing millions of trillions of times more than the Sun, all without ever placing these objects on a scale, relying instead on the universal language of gravity that connects everything in the cosmos through the elegant mathematics of orbital motion.